quiz in today's live session. So,
Ma'am, will you do any revision or?
I can even do a revision. So let me open the lecture notebook.
Yeah.
Mm, okay, I'm audible, right?
Yes, ma'am.
So, just before starting, something to clarify from our previous live session. So, some function like this, which is also called as a step function. Okay, so this has finite. So, if there is a function like this, then the function has finite discontinuities at this particular point. Okay, so someone was confused last time and was also kind of making me confused. So wherever there is a transition, you can prove that there is a discontinuity. For more details on this, you can check it out on Google. Okay, so this is, yeah, all right. So you can check for the definitions of continuity. I mean, you can try to practice this problem. So you can check for what a continuous function is and see why a particular function like this is discontinuous. Okay, you can verify for those things. All right, so this is just something that is there from the last week, but yeah, proceeding to this week. So the topics for the quiz are from week 5 to week 8, and the topics are as follows. So I think in week 5, what we have seen is systems, and we have looked at different properties of systems like causality, linearity, time invariance, stability, memory, right? And we have also seen anything that is both linear and time invariant is known as an LTI system. Okay. And in our and we have also specifically seen that LTI system is characterized by an impulse response h of t, and the output of this LTI system y of t is input convoluted with h of t, and this is where we have seen something known as convolution operator, which is an important operator, right? And I think in week 6 we more or less saw what convolution is. Yeah, we tried to learn more on this operator in week 6. Specifically, we have seen the properties of this convolution operator like commutativity, associativity, distributivity, right? And yeah, and we have also seen, how you can characterize an LTI system as memory system, causal system, stable system, given the impulse response. Yeah, we have seen all these things, right? And yeah, we have also seen something known as unit step response of LTI system. This is nothing but impulse response convoluted with the unit function u of t. Okay, so these are certain things that we have seen in our week 6. And moving to week 7, okay, we shifted gears and we went into something known as Fourier analysis. Okay, and what we mean by Fourier analysis, and in particular, we have seen Fourier series representation for any periodic signal. Okay, and also we have seen several properties of this Fourier series, effect of time scaling and shifting on this Fourier series. Yeah, and you know, uh, and also what happens to the Fourier series coefficients. So when any two signals x of t and y of t are multiplied, then their Fourier coefficients are convoluted. So convolution of Fourier series is also something that we have seen. Okay, and there's also something known as, so yeah, uh, basically in week 7 we have seen Fourier series and their properties, and in week 8 we have seen more on this Fourier series. Mainly we have seen the Pascal's theorem, yeah, Dirichlet's conditions, Okay, and more problems on how to solve this Fourier series. So these are the topics. Yeah. So starting from week 5, where we dealt with systems, where we have learned what systems are, their properties are. Week 6 is more on the convolution operator, like how can you do this convolution operator, learning convolution operator, and the properties of convolution, and then properties of specific systems, which are LTI systems. Yeah, unit response of an LTI system, impulse response of an LTI system. And so it's mostly on systems. Week 5 and 6 is on systems and convolution operator. And then week 7 we kind of shifted gears, and we have seen like what Fourier analysis is, what a Fourier series representation is, and how are periodic signals be represented in Fourier series. We have seen several examples on that, and also like we have seen how does a time scaling and shifting. So suppose if x of t has Fourier coefficients ak, then how does time shifting ct plus t this affect the Fourier coefficient? So all these things we have seen, right? And in eighth week, we more or less saw the main topics, which are Parseval's theorem, Dirichlet's conditions, and like I think Professor did several problems related to Fourier series. So these are the topics. So questions. So do you have any doubt in any of these topics? Specific doubt in any of these topics? Let me give you a minute to absorb. So these are the topics. Let's first evaluate week 5 and 6. Do you have any confusion with the topics from week 5 and 6? Yes, Subhash.
A brief discussion will be really helpful.
Brief discussion on which topic?
No. I'm saying like just brief through everything.
I can brief through everything, but then I think already our live sessions on week 5 and 6 summarize more or less these topics. I can even brief through now, quick brief, but then any specific questions even before going there?
Okay. So yeah, if there are no questions from anyone, then you will brief right now.
Yeah, I'll just touch upon every topic.
Yeah.
So
Okay.
if you want a detailed discussion, I suggest you go back to the previous live sessions and watch them,
Yeah. Sure.
because we did a rigorous summary on these topics in the earlier live sessions.
Okay. Thank you.
So yeah, any specific questions even before moving to the summary? No. Any specific questions regarding week 7 and 8?
Ma'am, could you brief the week 8 contents like Parseval theorems and all?
Parseval's theorem and Dirichlet's conditions, right? Yeah,
Yes,
we
ma'am.
can do that. Okay. So, uh, okay. So, week 8 assignment deadline is over, or is it still running?
Today, ma'am.
Today is the deadline for assignment. Okay, all right. I hope everybody is okay with your assignment, right? Yeah. Okay. All right. So, okay, let me just go through the brief summary. Maybe I'll go from back to front if that is okay with you guys. Let me start with week 8, and then maybe I'll first discuss on these topics, and then I'll discuss on the systems. Is that okay with everybody?
Yes, ma'am.
Okay. All right. So, okay. So what does a Parseval's theorem say? Let's start with Parseval's theorem. Important property is the following. Parseval's theorem states that, power, what is the power of a periodic signal? This we learned in our earlier lectures. So power of a periodic signal is 1 over T, right? Correct me if I'm wrong, but yeah, as I remember, so this is the power of a signal. It's the average energy in one time period, correct? So this is something that we already learned from our earlier lecture videos, that power of any periodic signal is the average energy between one time period.
Ma'am.
Okay? Yeah.
So, why the power is not the overall energy in a single time period?
No. So the power is like the definition of power itself is it's the average energy.
Okay. Because in earlier in school days, generally in mechanical concepts, the power is defined in that way.
Oh, I see.
So
Okay.
in
Okay.
here, it is the definition, isn't it?
Okay. Yes, yes. For any signal, the power of any periodic signal, it's the average energy within one single time period. Okay. And how do we take the average? So we evaluate. So average is like you sum it over all the time periods divided by the entire time period. So here, like if it is in the discrete time domain, but since we are working with the continuous time domain, we replace sum with the integration, and this is the average energy within one time period. Okay. Now, okay, so this is what it is. So earlier, how are we doing this? So suppose if you are given any periodic signal sine t, how do you calculate the power? You calculate the power as you find the time period of the signal. What is the time period of the signal? So this can be written as sine t 2 pi f is 1, which implies f is 1 over 2 pi, which also implies t is 2 pi, right? So the power of this given, the time period of this given signal is 2 pi. So this can be written as the power is 1 by 2 pi integral minus pi to pi mod sine t square dt. So this is how we were evaluating the power earlier, right? But here it kind of involves doing some calculation on your, you have to calculate this particular integral. Okay. Likewise, suppose if you are given some signal sine t plus cos t, the way you will evaluate the power for this particular maybe x1 of t. So power of x1 of t is evaluated as 1 over 2 pi integral minus pi to pi mod sine t plus cos t whole square dt, and it requires you to evaluate these integrals, right? Now what, here comes the solution to this. What Parseval's theorem states is that the power of any periodic signal, okay, so p x of t, where x of t is a periodic signal, let me just denote it by px because it's not depending on t, power won't be dependent on t. The power of this signal is, which is 1 by t integral minus t by 2 to t by 2 mod x of t square dt. This is just equal to the sum of all its Fourier coefficients. Okay, so this is an important property or the theorem. So what Parsells theorem states is the power of any periodic signal is just the sum of the squares of its Fourier series coefficients. So now using this integration can be easily simplified, right? Because we know sin t can be represented as e power jt minus e power minus jt by 2j. Cos t can be represented as e power jt plus e power minus jt by 2, which in other words is e power jt into 1 by 2j plus 2 plus e power minus jt times, sorry, yeah, what is our fundamental frequency? Omega naught is 2 pi by t, which is 1. So sin t plus cos t has the form sum over k from minus infinity to infinity ak e power jk omega naught t, where our omega naught is 1. So this is minus infinity to infinity e power jk t, right? So equating this with whatever we saw earlier, so this is e power jt times 1 by 2j plus 1 by 2 plus e power minus jt times 1 by plus 1 by 2. Once we have this, you can say that your Fourier coefficients a1 are 1 by 2j plus 1 by 2, a minus 1 is 1 by 2 minus 1 by 2j, and ak is 0 for all k not equal to 1 or minus 1. Once you have the Fourier coefficients, instead of calculating, this entire integration, you can just sum. So this integration would be equal to sum over k from minus infinity to infinity mod ak square by Parsells theorem, and this is equal to just a1 square, sorry, mod a1 square plus mod a minus 1 square. So that's the whole idea. Okay, so where mod is the absolute value. Okay, so this is the whole idea when it comes to the Parsells theorem. You can just plug in and you can evaluate the power. If you want, you can calculate this separately, and you can verify that both turns out to be equal. Okay, so yeah, to summarize, Parsells theorem states that the average power of a period, or the power of any periodic signal, is equal to the uh, squares of the magnitude of the Fourier series coefficients. So that's the idea. Okay, so hope it is clear. So that is with the Parsells theorem. So let me move to the Dirichlet's conditions. So why Dirichlet's conditions are important, and where, how do you, so uh,
Ma'am,
yeah,
if we try to calculate the power of a finite signal, then
what you
it will
mean
be,
by the finite signal is not periodic, right?
yeah, yes, correct.
Okay, so
So it's not applicable.
Parsells theorem is given only for periodic signals.
Yes, okay.
Only for periodic signals there is Fourier series representation, and only when you have a Fourier series representation you have the Parsells theorem. Okay.
Yes, yes.
So Dirichlet's conditions. So what Dirichlet's condition states is, so any periodic signal.
Hey,
Yeah,
So,
someone.
yeah. So, is there
Yeah.
any proof for the classwork?
Uh, Maybe professor did it in your lecture video, but yeah, this live session is not meant to derive any proofs. Okay. So yeah, any periodic signal x of t with some period t. When we have period t, we have the fundamental angular frequency as 2 pi by t, right? So for any periodic signal, we have the Fourier series representation. In other words, we can write that this signal as ak e power jk omega naught t. So this is Fourier series representation, right? Now question. So suppose, like when you say that, this is exactly equal to this, you should also verify. So this is on your right hand side. On your right hand side, you have the summation. Usually certain summations are not converging, right? As in, suppose if you have sum over k from minus infinity to infinity ak, where ak is 1 for all k, this is a diverging sum, as in the whole sum goes to infinity, right? When do we say a sum is converging? We say a sum is converging if that sum, you know, uh, maybe some f of t or k, some function, if this converges to some value, say L, that is less than infinity, then we call such a sum to be converging sum. Okay. In other words, uh, you know, the whole sum kind of sums up to some constant L that is a finite value. Okay. But whereas in case of diverging sum, when we say something is diverging, it implies, the end value is going to be infinity. That is what we mean by something is diverging. Okay. Now, when you say that there exists a representation for x of t as as a sum of infinite terms, okay. Any question that one would ask is the sum on the right hand side, is this even a valid sum? Is this a converging sum for, is this converging for all values in t? As an example, when you take t as 0, x of 0 is simply minus infinity to infinity ak 0. So this is just ak's, right? Now the question is, does this sum converge to the value x of 0? Okay. So we are writing some nice representation, which is good. We are finding the Fourier coefficients, which is also good. But now the question is, so one way you're doing, so you're trying to find your AKs from any given signal x of t. You're trying to find your AKs by using this representation 1 by t integral minus t by 2 to t by 2 x of t e power minus jk omega naught t dt. So you're finding your AKs like this. Once you find your AKs like this, you're trying to represent your given signal in this form, in this particular form, right? So when you represent this in this particular form, the next question you would like to ask is, for every value of t, is this sum even a converging sum? As in, for every value of t, so for 0, when t is equal to 0, the sum on the right hand side would just become this. So is this equal to x of 0? Likewise, when t equal to 1, x of 1 is minus infinity to infinity ak e power j 1 omega naught t. So is this equality true? I mean, does this sum converge to x of 1? I mean, like when you solve this summation, will you get x of 1? Okay, so these are the certain theoretical questions that one can ask when you write in terms of sum. Like when you write something in terms of sum, and when the sum is running, you know, running to infinity, then definitely one should ask this question. So when something is taking you to the infinity, does the sum even converging? If it diverges, then there is no point in doing such things. So you have to come up with a valid sum. Okay, the sum should be valid in the first place. So this is what is answered by Dirichlet's conditions. What Dirichlet's condition states is that the sum is not always converging. Okay, so what Dirichlet's condition states is, so you can write x of t as sum over k from minus infinity to infinity a k e power j k omega naught t. So you can write like this only under specific constraints or only under specific conditions. Okay, so you cannot write this. So one thing is sure, for a periodic signals, Fourier series representation is not there. In periodic signals, we have some signals which satisfy Dirichlet conditions and we have some signals which do not satisfy Dirichlet's conditions. For the signals which do not satisfy Dirichlet's conditions, this is not a valid representation. Okay, only for the signals which satisfy Dirichlet's conditions, the sum we are writing on the right hand side is a valid representation. And what are those conditions that you can verify? So within a finite period t, the first condition is x of t should be absolutely integrable. In other words, okay, and the second condition is x of t within a finite period should have finite number of maxima and minima. And the third condition states x of t within a period t should have finite number of okay, so these are the three conditions. So as said, a periodic signals can never have Fourier series representation. Even for periodic signals, only the signals that satisfy these Dirichlet's conditions have this valid representation. The signals that do not satisfy Dirichlet conditions, for those signals, this is not a valid representation because the sum never converges to this value. So it's not a valid representation. Okay, so that's the idea. So to summarize, you can break it like this. So Fourier series representation for aperiodic signals is not possible. And for any periodic signal, you have to first verify if all these three properties are satisfied. If and only if these three properties, so these are necessary, these are sufficient conditions. So if these conditions are satisfied, then definitely Fourier series is a valid representation. Okay, so these are like sufficient conditions. What I mean by sufficient conditions is, for a Fourier series representation to be a valid representation, it is sufficient to satisfy these three conditions. Okay, so those conditions are known as Dirichlet's conditions. Okay, is that all right?
Yes, ma'am.
Okay, so I
Ma-
think, yeah.
So, how can we convert the real signal into so that it can obey the Fourier series things, because all real signals are aperiodic, right?
All real signals are aperiodica. Who told you that?
Yes, ma'am, because it won't be infinitely long. Right?
Who told you that real signals cannot be infinitely long?
Um,
No, your
because,
understanding is wrong. Real signal can go from minus infinity. Real signal does not mean that the thing. So no, no, your understanding is wrong. Yeah, you
no,
can look about it. Okay.
the time it elongates is only finite. No, ma'am. It can't be infinitely made on or off. So, I mean, it should be on for a certain duration of time only. Right?
No, that's not true. Uh, that's not true. So, but to answer your question, so anything that is running from, so any signal that is, uh, yeah, any signal that, maybe sine t, if you take a sine t signal, it runs across the infinite time. Sine t is the signal that you use for a lot of transmissions, which is a real signal. Okay, so but like when you work with the actual practical systems, what you tend to put is, you tend to put a bound on, the transmission, but still that's a valid real signal which runs across the entire time axis.
So we
So
assume it
maybe you
runs.
focus on minus t to t in real systems, or maybe some t to, some 10,000 t. Okay, so this 10 larger time in your real time, you consider something to be infinity.
Yeah, yes.
Yes,
Okay.
this requires some level of experience to understand, but to answer your question, so there are infinite length systems, but when you implement the practical systems, you put a large condition on t which you assume to be infinity.
Yeah, yes, ma'am. So now it can be put into a Fourier series things,
Yeah,
transformation.
yeah, any periodic signal. So when you look for the periodicity in real time, what you tend to see is, suppose if you're transmitting from t to 2t, okay, so you look within this range if the signal is periodic, because according to you, your transmission time, is running within this interval. So right from the beginning of the time to the ending of the time, if the signal is something like this which is periodic, then you assume this to be a periodic signal. But if you have something like this, maybe your start time of the system is t and your end time is maybe some 10,000 t. Okay, so if you have something like this, then definitely this will not have a Fourier series representation.
Yeah, yes, ma'am.
Okay, is
Yes,
that
ma'am.
okay? Yeah,
Yes, ma'am.
so yeah, maybe your understanding about the real signal was little incorrect. Think about it a bit. Okay,
Yeah, yes, ma'am. Okay.
all right. So yeah, I think we are good with the Dirichlet's conditions. I think Professor solved several problems in your lecture videos, which you can go through. Week 8 is okay, right? Any questions in week 8?
Yes, ma'am.
Hmm?
Practice assignment question.
Hmm?
Practice assignment question.
Oh, practice assignment questions. Okay, let me open the practice assignments. Yes, which practice assignment question? So there are a couple of questions 11 and 12 which is for you guys to discuss among yourselves. So I'm not going to solve them. I wanted you guys to discuss among yourselves, okay? Other than that, questions 1 to 10, if you have any questions, we can discuss.
1 to 4.
1 to 4. What happened with that question? So, what is the difficulty? I think in our last live session, we did a similar problem, right?
Yes, ma'am.
So, Satyam, right? Satyam, are you asking this question?
Yes, ma'am.
Yeah, I think you're facing some difficulty in, expressing these signals as the exponential signals. I think even in the last live session, yeah, maybe you need to practice more on how you can do this, but I'll try to do this problem. So, suppose if you're given this signal cos t plus 5 sine 4t. First question, what is the fundamental frequency of this particular signal? How do we solve for the fundamental frequency? Let's call this as x1 of t and this as x2 of t. x1 of t has fundamental period t1. How do we find that? 2 pi f1 is 1. f1 is 1 by 2 pi. t1 is 2 pi. x2 of t, let's say it has a fundamental period t2. 2 pi f2 is 4. f2 is 4 by 2 pi. 2 by pi. So t2 is pi by 2, right? Now, how do we find the whole period? Suppose we already did this in our earlier session. Suppose if a signal is a sum of two periodic signals, the first question that we ask is x1 periodic? Sorry, is x of t periodic? How do we answer this? So we try to find the fraction t1 by t2. Yeah, and the fraction is 4, right? So the fraction is a rational number, and hence since this is a rational number, the given signal x of t, which is the sum of two periodic signals, is also periodic. Now how do we find for the fundamental period of x of t? So t is equal to, so this fraction t1 by t2 is equal to 4, which implies t1 is equal to 4 t2. This is equal to the fundamental period t of the sum of two signals. And what is, so t1 is 2 pi. What is 4 t2? 4 into pi by 2, which is also 2 pi. So the fundamental period of the given signal is 2 pi, and fundamental angular frequency omega is 2 pi by t, which is 1. Is that okay? First question. This is something we have seen in our early lectures. Is this okay?
Yes, ma'am.
So now moving to the second question. You're supposed to find the Fourier coefficients. So as I discussed in our previous live session, you can do this as follows. So since this is a periodic signal, this has the representation x of t as k from minus infinity to infinity, ak e power jk omega naught t. What is our omega naught? It is 1. So this is k from minus infinity to infinity, ak e power j omega naught, jk t. Right? When you expand, how does this look? This is a0 e power 0 plus a1 e power jt plus a2 e power 2jt plus a3 e power 3jt and so on. And on the negative axis we have a minus 1 e power minus jt. Correct? Just the expansion representation. Now we have to find the Fourier coefficients. We need to find them. How do we find them? So we know the nice formula. Yeah. So you substitute your signal x of t in this and then you find the integration. That is one way. Or the easiest way when you have cos or sine signals is x of t. So let me call this as star, this summation as star. Since x of t is a periodic signal, and also you can find out that this particular signal satisfies Dirichlet's conditions. It is very evident. Okay, so you can find out this minus t by 2 to t by 2 mod x of t dt. You can see this to be infinity, and just by plotting this you can find that this particular signal within a period has finite maxima minima, because the maxima is only uh, there is only one maxima. You can upper bound this by 1 cos t by 1 and sin t by you can figure out that there are only finite number of maxima minima. And also you can plot this and see within a period this has only finite number of, this has no discontinuities at all. I mean, this particular signal won't have any discontinuity, zero discontinuity. So the Dirichlet conditions are obeyed. Hence, this has a valid Fourier series representation. Okay. So hence the given signal can be represented like this, the equality that is there over here. But then in order to write it in a nicer form, you have to identify this Fourier coefficients. You have to calculate these Fourier coefficients. How do we calculate this Fourier coefficients? We have this nice formula. So this is like one way to do. You can evaluate this integration, and this is one way to do. But or the other easiest way is, so write down the signal cos t plus 5 sine 4t. We know cos t can be represented as e power jt plus e power minus jt by 2, plus 5 times this can be represented as, so when you split and write this is 1 plus 2j by 2 e power jt, 1 plus 2j by 2 e power minus jt, plus 5 by 2j e power 4jt okay, let me call this. Yeah, so this is another form of x of t. So this can be simply written as like this. Okay, and what our analysis tells is this signal is a periodic signal and it has a valid Fourier series representation, hence it can be written as star. So star and triple star are in general equal, because any periodic signal has a valid Fourier series representation. Also, this satisfies the Dirichlet's conditions. So star star and star should be equal. If these two should be equal, then what are the coefficients? So, like when you say this particular equation and this equation are equal, what does it means? It means, since e power jt, e power minus jt, e power 4jt, e power minus 4jt, they are valid exponential signals. In order for these star and star 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 to be equal, the coefficient should be equal. Then what does it mean? Coefficients to be equal implies a1 is equal to 1 plus 2j by 2. Okay, and a minus 1 is equal to 1 plus 2j by 2, and a4 is equal to 5 by 2j, and a minus 4 is minus 5 by 2j, and ak is 0 for k not equal to 1 minus 1 4 minus 4. Okay, so summary, what did I do? So this given signal is a periodic signal, hence it has this Fourier series representation. I just expanded out the Fourier series representation. You can either calculate the Fourier coefficients in this Fourier series representation by calculating this integration, or another way is try to write down the given signal in a different form. So I'm not doing anything, I'm just trying to write down the given signal in a different form. When I write it in different form, what I get is the sum of exponentials. And since this is a periodic signal, it has a valid Fourier series representation. This particular x of t should be equal to the expansion of the Fourier series. And when these two are equal, what it means, the coefficients with respect to the particular exponential signal should be also equal. And equating them, we get the Fourier coefficients to be something like this. So this is like the simple way to, if you're still confused, you can still try to, find out this integration expression. That is always a valid way. Yeah, so that is what it is. You can try to work out more on this if you have more doubts, but this is all it is there to say this. Okay,
Yes, ma'am.
so week 8 is okay, right? Any more questions?
Ma'am,
Yes.
in the first question which we solved,
Mm.
uh, so when we have the time periods as multiples of each other, is it okay to take the biggest time period and say it is the answer?
Time periods are even finding. So so the honest answer for this is you have to take the I think GCD of the two time periods, I guess. Okay, so
Yeah, yes.
when you even try to do that, you get something like this. So you get the exact same answer. So instead of confusing someone with GCD or LCM, because taking GCD of fractions is little hard, you have to take the GCD of numerators and LCM of the denominators. So I don't want you guys to be confused with that. So you get the exact same answer. That is also another thing. If you just try to Google it, how to find the time period of sum of two signals, you get what exactly you're telling me. But I'm just giving you another simple way of doing that.
Yes, ma'am.
Okay. So instead
Yes.
of being always confused with GCDs and all, like all you have to do is, given any two operators, all you have to do is, given any two functions with some operator in the middle, all you have to do is calculate the two time periods differently and try to see uh, if their uh, uh, fraction of the time periods is a rational number. If it is rational, then the given the original signal is periodic. And once you have that, the entire period is just like try to equate the time periods using this fraction, and you get it, instead of being confused with LCMs, GCDs and all. This is like a better way. And at least for me, this is a better way. If you're happy to do GCDs, I think you can. So it's the GCD of T1 and T2. So if you are good to do GCD, you can still do GCD. Okay.
Yeah, yes. And ma'am, in the second question, final expression.
Yes. You mean
So,
this?
yes, ma'am.
Mm.
So here we are getting the k in terms of pairs, right, ma'am? Like 1 minus 1, 4 minus 4.
Mm.
Why is that, ma'am?
So there is nothing wise like that. So cos t is represented in that way, and sin t is also represented in that way. The reason is simply that, suppose if you have maybe um, maybe say cos t plus sin t, cos t by 2j times sin t, or cos t, or minus j cos t. Suppose if you have something like this, okay. So what is this? So this is e power jt plus e power minus jt by 2j plus e power jt. This and this gets cancelled, and what you have is, you only have a1 here. Okay. So it just happened for this problem, they came in pairs. That's all. There's nothing specific to that.
Yes, sir. Okay. Yeah, yes, ma'am.
Okay with Fourier series? Any more questions?
And
I'm planning to take only till 9:30. My health is not really good, so yeah. Maybe we can other topics. So after 9:30, we can discuss maybe on the next live session. But yeah.
yes, ma'am.
Yes. Somebody had some questions. So.
Yeah, ma'am. Ma'am,
Mhm.
yeah, ma'am, I understood. I got a picture of what is Fourier series and all, but still, what I struggle is what is convolution. I'm unable to get the intuition.
Okay, I think convolution can be thought of as an operator. Okay. But the idea where it is coming from, I think I also derived it in our earlier live sessions. So I don't have the exact derivation in hand now. But you can go back and look at the live session that we discussed this. I remember doing it in two live sessions. Suppose when you transmit any delta function into a linear and time invariant system. Okay. So let me say that the system has some transformation which is given by this function f. Okay. And the given system is a linear time invariant system. Okay. So the output of this particular specific thing is f of del of t. Okay. Let me call this by h of t. Okay. So f of del of t is h of t. F is linear. Also, it is time invariant. Yeah. This is unit impulse function. This is also known as the impulse response. The response of the system when you send impulse function into the system. Okay. So this is something that you need to understand. So for an LTI system, there's something known as impulse response. What we mean by impulse response is when you transmit an impulse function into the LTI system, the LTI system does apply some transformation over it, and this is known as the impulse response of the system. Now, you take any signal x of t. X of t can be represented as x of tau del of t minus tau dt. So x of t can be represented as sum of unit impulses. This is something that we have seen multiple times. We also solved problems on this, right? I mean,
Yes,
are
ma'am.
you agreed on this? I
Yeah,
mean, we know this. This is something
yeah,
that we have done.
yeah.
So now, when I transmit x of t into this LTI system, the same transformation f, which is linear and time invariant, gets applied, this transformation will be applied on this input signal x of t, and the output is f of x of t. Correct? Yeah. And we
Yeah,
know
ma'am.
this is linear and this is also time invariant. Okay. So let's try to evaluate f of x of t. What is f of x of t? So this is, since x of t can be written as sum of the impulses, this can be written as minus infinity to infinity x of tau del of t minus tau d tau. Correct? And remember, f is a linear function. Yeah. So when we say linear, this f function can be taken inside the summation. And this is your output signal y of t. So we are looking in the t domain. So this tau values will be constants. So f of a uh, f of some a times x of t plus b times x2 of t is a times f of x1 of t plus b times f of x2 of t, right? Because f is a linear system. And since we are working in the t domain, the tau values will be like coefficients for the given signal, and hence this f can be taken inside, and this is t minus tau d tau. This is because the reasoning is since f is linear. Okay, and also since f is time invariant, when you pass del of t, the output is f of del of t, which is h of t. And when you pass some del of t minus t naught, the output will also be h of t minus t naught. This is the property of time invariance. Correct? Because of that reason, so this is x of tau, h of t minus tau, d tau. Right? So what did we do? What we did is, when you transmit del of t into an LTI system, your output is h of t. This is only true for an LTI system. Yeah, because f can be taken inside because of the linearity, and this happens because f is time invariant. If any of these two constraints are failed, this may not happen, right? So when we transmit del of t into an LTI system, let me call this transformation as f of del of t is equal to h of t. This we are calling an impulse response. So when we have this, when you transmit another signal x of t into an LTI system, we just saw that the output y of t is nothing but integral minus infinity to infinity x of tau h of t minus tau d tau. Yeah, this is something that we proved. Are you with me? Hello?
Yes, ma'am.
So this particular operator is named as a different operator, that is the convolution operator. Okay. So this particular form is given an operator name which is known as the convolution of two signals x of t and h of t. Is that okay?
So we are just replacing the impulse signal with some other signal.
We are not replacing the impulse signal with some other signal. We proved that for an LTI system, if the impulse response is h of t, then for any other signal, the output will be this.
Oh, okay. Yeah, so we are somehow mapping every signal's output with impulse response.
Yeah, because any signal can be written as sum of impulses, right?
Yeah, yeah.
And when h of t is the output of the impulse, output output for an impulse response when passed over an LTI system, this is the output when any signal x of t is passed over an LTI system. And for this particular output, we are naming it using an operator known as the convolution. That's all. Convolution is defined in this way. So convolution between any two signals x of t and h of t is defined as, is that okay?
Yeah, ma'am. Got it. Thank you. So we are doing all this because we can represent any system's characteristics with its uh, impulse responses.
Only for LTI system.
Yeah. Okay. Yeah.
Okay.
Yeah, ma'am.
Is that okay? Any questions regarding Fourier series? Let me go back to the topics. So I hope more or less. So there is a nice table in your lecture notes for how effect of time scaling and shifting affects the Fourier coefficients. We also gave, every property is given as assignment problem in your assignments. So go back to solving your assignment problems, if you want to learn about how time scaling and shifting affects your Fourier coefficients. Okay, so week 8, week 7, I hope you guys are good, right?
Yes, ma'am.
All right. So I think week 6 and 5 we covered like so many times. Whatever we have seen now, we are okay with what this convolution operator is and what we mean by the commutativity property of convolution. Can someone say?
We can change the order of the system.
So commutativity implies x of t convoluted with h of t is same as h of t convoluted with x of t. What is associativity?
Changing the position of brackets.
So x of t convoluted with h1 of t convoluted with h2 of t is same as x of t convoluted with h1 of t convoluted with h2 of t. In other words, what this says is, suppose you have two LTI systems, h1 of t and h2 of t. The output at this point, y1 of t, is x1 of t convoluted h1 of t. Now, this output is the input to the second system. So, this is x1 of t convoluted h1 of t convoluted h2 of t. This is same as passing the input signal x1 of t into an overall impulse system which has impulse h1 of t convoluted h2 of t. Then your output y of t would be x of t convoluted with h1 of t. So this is true for any LTI systems. Okay, so that is what we mean by the associativity. Likewise, distributivity, x of t convoluted h1 of t plus h2 of t is x of t convoluted h1 of t plus x of t convoluted h2 of t. Okay, properties are simple, but for convolution you guys need to practice more and more problems. As said, while you are trying to understand addition, subtraction, multiplication, division, you may have experienced a lot of difficulty during your childhood, but once you understand it, it's pretty straightforward. Even convolution is a new operator that you are learning now. So once you solve more and more problems, it just becomes handy. Okay, and yeah, convolution, I hope things are okay. And suppose if you are given an LTI system with impulse response h of t, you know how to say if it is a memory. It is a memoryless system if h of t is equal to 0 for all t not equal to 0, then it is memoryless. It is causal if h of t equal to 0 for all t less than 0. It is stable if minus infinity to infinity h of t dt if this is less than infinity. Okay, so these are certain conditions which are also available in your class notes, and we did enough problems on this. I think it is good. Unit response of an LTI system is when the input is unit step function. So it is just u of t convoluted with the impulse response u of t convoluted with h of t. That is known as the unit response of an LTI system. Okay. All right. I think week 6 also we are fine, right?
Ma'am,
Yes.
invertibility.
Invertibility. All right. So invertibility. What is invertibility? I think we discussed earlier multiple times. Suppose An LTI system is invertible if you can come up with an impulse response H inverse of t, okay, then we say the given LTI system is invertible. Invertible if H inverse exists. Is that okay? And how do we check for the invertibility for any invertible? It's just a function, right? H of t is a function. And how do we say an inverse of a function exists? It should be one function and it should also be onto function, right? So those are the conditions that you may have to verify. It should be a bijective function. You know how to check for a function if it is inverse or not, right? There is something known as bijective function. So bijective functions are invertible. So just check if the given impulse response h is a bijective function or not. That's all. That is all there is.
And ma'am, if the function is not stable, it is always not invertible, right?
There's no rule like that.
Um, in in one of the lectures, I think professor told like this.
Oh, is it? I'm not aware of it. Maybe you can forward me that particular point. I'm
Yeah,
not sure of it. As far as I know, I don't know about this. Okay.
yeah, yes. And ma'am, in convolution, is changing the position of the t, the minus t, uh, is same, ma'am? Will it
As
change
in,
the equation?
you are asking me, so x of t convoluted with h of t. Now you are asking me x of minus t convoluted with h of t, right?
No, ma'am. X of t into h of t minus tau, is it equal to?
Uh, so you are asking me question, is this equal to y of t minus tau?
No, ma'am. Could you please go scroll down, ma'am, little bit?
Yeah.
The Yeah, here, ma'am. Yes, the convolution part. Yes,
This
ma'am. Here,
is, mm,
yes, ma'am. Here is changing the. Here we have minus tau on the h thing, right, ma'am? In the bracket.
here. Mm, oops.
Yes, ma'am. So putting it on the bracket of the x, will it also same? Is it also same?
Oh, so you're asking me if this is, so this is also equal to minus infinity to infinity h of tau x of t minus tau d tau.
Yes, ma'am.
Because convolution is associative, right? So this is also equal to h of.
Yeah, yes, ma'am. So it's same, right, ma'am?
Yes, yes.
Okay. So
You can
it can
use any way.
it can be thought of we are swiping the signal by a impulse response, and the other as swiping the signal through a impulse response.
Mm.
Yes, ma'am. Okay.
Okay. Any more questions? Okay, good. So I hope even week 6 content is okay. Week 7, yeah, I think we discussed several times. Causality, we know how to see if x of t, uh, I mean, suppose if you pass x of t over some system, and if you get y of t, where this is some transform t, y of t is t x of t, if this y of t depends only on the uh, present and past values of the input, but not on the future values of the input, then 1 second, sorry. Yeah, so if the output depends only on the present and past, not on future, then such a system is known as causal. For memoryless, it should not depend on future, it should not depend on past, it should only depend on present. And for stability, bibo stability, how do we check that? Bounded input should yield bounded output. I mean, there are several examples that we did enough examples. You can try doing them again. Time invariance, we know how to check for that. Uh, you know, if your output is y of t, when x of t is transmitted, imagine when x of t minus t naught is transmitted, your output is y1 of t. If this y1 of t is equal to y of t minus t naught, then it's a time invariant system. Again, we did enough examples with respect to this, also linearity. So yeah, I hope these things should be okay with you guys. So these are the topics for your quiz. It's with the practice. Lot of things require practice in these topics. So convolution, Fourier series, properties of the signal systems, everything requires practice. So yeah, you have to practice a lot. That's all. That's all from my side. I'm here for another 5 minutes. If you have any questions, you can ask.
Ma'am,
Yes.
so all memoryless systems is causal system, right?
Yes.
Yes. Okay.
Ma'am,
Mm.
could you explain question 7 of wicket practice?
Question 7 from week 8 practice
Yeah.
assignment. Mm. What is the difficulty? So there is some signal which is told in the problem itself that x of t is periodic with period 2, and it is defined in one particular period as follows. So x of t is given as 1, 0. In other words, the signal is something like this. Yeah, this is what we mean by x of t being a periodic signal with period 2, and it is defined in one period, one particular period from 0 to t, as given. Now the question is to find a0. What is a0? Right? And what is your period? Your period is 1 over 2. And what is minus t by 2? Minus t by 2 is minus 1, 2, 1 x of t dt, which is 1 by 2. It's all right. Is that okay?
Yes, ma'am.
Yeah, any more questions? Please practice, please discuss with your friends. I think exams are the times when you make real friends. uh, Tough times always will push us towards something that we may not do during our regular times. So yeah, make some good friends, do some combined studies, practice a lot. Things should be fine. Okay. Yeah, I would like to take a break for today. Yeah, Muthu.
Um, Ma'am, so when will we get the mock questions?
Also, one more thing. From week 4 to week 8, let me guys let me know that if there are any mistakes with respect to the assignment problems. I mean, let me know if some re-evaluation is required, as in there are certain times where the option is incorrect but your answer is okay, right? So maybe the given question itself is wrong. So let me know if there are any such things from week 4 to week 8. Please let me know by tomorrow morning. You can discuss among yourselves, and maybe collectively, since you have this WhatsApp group, do one thing. Uh, One of you just try to take all those re-evaluation questions and please email me. Okay. Yeah. So yeah, if there's some mistake from our side, we will give full marks to everybody. So let me know if there are any such questions which requires re-evaluation in the assignments. Okay. There will be no for quiz 2. There won't be any questions from week 1 to 4. Maybe for the end sem there will be. Okay. All right. So Muthu, you were asking me something.
Yes, ma'am. So when will we get mock questions?
Mark questions as in
Mock, ma'am.
marks. Okay, you guys tell me what questions need re-evaluation. Once I sign it off, I think you will get your marks in a day.
No, ma'am, not marks. Mock for quiz 2.
Quiz 2 is same as quiz 1. It'll be for 50 marks,
No,
25 questions.
ma'am. Ma'am, in
MOCK.
other subjects, they give
Oh,
something like a
mock
mock test.
exam. Okay.
Yeah.
I think for signals and systems, we don't have any mock.
Oh, okay, ma'am. Yeah.
Okay, so
Then can
it's
we
a direct
do
test.
uh, questions only on the next session?
Questions, yeah, if you have any specific questions, yeah, assignment questions are enough. There's nothing extra I would like you to do apart from your. So just go through your assignment questions. If you have any difficulty with the assignment questions, we can discuss that. Okay. Also,
Yeah,
the
yes.
quiz level will be similar to the assignments. If you're good with your assignments, you'll be doing good with quiz. So yeah, no mock test or anything. So direct exam on 7th. Okay.
Yes.
Okay. Okay. Thanks. Okay. Bye. Okay, guys.
Yeah.
Yes.
Bye.
Thank you.
Yeah, good night. Yeah.
Thank you,
Good
ma'am.
night.
Thank you.
Take
Good
care,
night.
ma'am.
Yeah.
Thanks.
Thank you.
Thanks for taking the session despite of your ill health, man.
Yeah, ma'am.
Yeah.
Yeah,
Thanks.
yes, ma'am. Thank you.
Subhash,
Ma'am.
do you have any questions? Or yeah, I would like
Oh,
to.
yeah, not a question exactly, but I have been thinking to get some advice from you from long time.
Okay.
Okay, yeah. Okay, see, I have been. I don't know how to put this, but I am an all full-time student, standalone student.
Okay.
So yeah, I have cleared my JE, but despite of
Mm.
clearing it due to some mistakes in JOSA, I have been as online student.
Mm.
So yeah, how I could make the best use of this online degree and what opportunities can I search in the next terms on base of this course?
Hmm. Okay, so one immediate advice that I could think of is I think there is some privilege for online students coming to IIT Madras and doing something here during their final year. Is that true?
Man, everything is tentative and they are saying one thing. I mean, each and every day those things are changing. We can't rely upon that.
Mm-hmm. Okay, so I think so. Which year are you in?
Yes, ma'am. I'm in second, ma'am. Will you stop the recording?
Okay, let me stop.